I welcome you all to the last session, Polya's counting theorem. Let me explain about the basic notations that are needed for Polya's counting theorem. Take capital D and R as a finite sets and P be a permutation group formed using the set of elements of D. Rho is called, W of rho is the element of R, and W of rho is called as weight of rho or else content. Content means weight. So either you can use weight or content. Now, if there is a mapping from D to R similar to this, writing sequence of elements of R. Sequence means writing elements in an order separated by commas. So I have to write sequence of elements using the elements of R. How many elements it should contain? This sequence should contain modulus of D elements. Modulus of D means number of elements of D. In this example, D contains 3 elements. This mapping can be expressed as sequence. How I can express? The first element maps to S. Second element maps to D. Third element maps to T. So, the mapping can be expressed as a sequence S, T. And weight of this function, total weight, capital W of F, is nothing but product of weight of F of D where D belongs to. Weight of F of D, mapping. F of D means this S and T. And their corresponding weights are multiplied and to get a weight of F. So weight of a function can be obtained by multiplying. Pi represents multiplication of weight. W represents weight of this element. What is this element? If A is there, F of A is S. So F of D. D is an element of capital D and their images are denoted by F of D. Image of A is S, image of B is T, image of C. And weight of these elements are taken together and multiplied, and final answer is taken to be weight of F. In the last video we have seen equivalence classes. A function belonging to a class, all the functions which belong to a same equivalence class will have same weight. Coming to the terminology used in Polya's theorem, any function from D to D is called as configuration. Hereafter we won't represent this one as function. We call it as configurations according to Polya. Omega of rho, weight of rho, is expressed as this weight will be taken to the power of x. This x is a dummy variable. Only the power makes a importance. So weight of this rho will be taken to the power of a dummy variable x. Then we are going to write two series. One is A of x and B of x. The A of x is said to be counting series. B of x is configuration counting series. Series in the sense it is a summation of some elements. So x of q, I told that x is a dummy variable. Q is the weight of the element of R. Weight assigned to rho. Rho is the element of R. What is its coefficient A of q? Number of elements having with weight x of q. So number of elements having the weight q. That is counted and multiplied with the coefficient. In the very first session of enumeration, I explained that in a series the coefficient makes importance and always the variable is a dummy variable. It has no significance. The power and coefficient makes importance. And the second series here, it is related to the weight of elements in R. Here it represents to configuration, that is F. So number of configurations, x to the power m represents number of configurations, and bm number of different configurations with a weight x to the power m. With this, let us come to Polya's counting theorem. This is the actual statement. So what we are trying to find? Finally we are trying to find a series. That's it. B of x. What we done in the earlier we have found the series to count the labeled and unlabeled graphs. The same criteria, but in order to find the series, Polya's counting theorem gives the easiest way to find the series. In the last sessions before Polya's theorem, we have expressed series and we have found the coefficients to count the labeled graphs and unlabeled graphs. The same thing, but there finding series itself is a tedious task. But here, according to Polya, if you follow the instructions of Polya's theorem, it is easy for me to calculate the series p of x. So when I express the series, then it is easy to count the coefficients of x to the power 1, x to the power 2 to find the number of graphs, specified number of graphs. So we are going to find the series b of x. The required series is b of x. How we are going to find this b of x? For that, what Polya is suggesting is, first you find a figure counting series. A of x is figure counting series. Find a of x, then a of x to the power I for each y. Then use that a of x for each yi that are used in cycle index. What is cycle index? Cycle index is nothing but, with respect to a permutation p, we used to add all the cycle structures and divided by total number of elements. Now you replace y1 by a of x to the power 1. y2, replace y2 by a of x square. The power and the suffix are related. I. y3 is replaced by a of x. So first you find a of x, then you find a of x square. Just replace all x by x square, you will get a of x square. Similarly, find a of x cube, etc., a of y to the power k, and substitute in your cycle index. So what you need is, you need to find cycle index. If you know how to find cycle index, then only you can use Polya's theorem. If you want to find a cycle index, you must know how to write a cycle structure. If you want to write a cycle structure, you must know how to write the permutation. That's what the link. So first you write the cycle structure. In the cycle index. In the cycle index, you try to replace the variables y1, y2, y3 by a of x to the power 1, a of x to the power 2, etc., a of x to the power k. Then that will give you a required b of x. That's what given in Polya's theorem. Using Polya's theorem, we are going to find a series for simple graph, then directed graph, simple directed graph, and for multiple graph. So we are going to see the enumeration of graphs. Enumeration means counting the number of graphs available in that particular category. So we are going to find the series in order to find such enumeration using Polya's statement. Step number 1, what I have to do is, I have to find cycle index. Then I have to find a of x. Then in that cycle index, I have to replace the corresponding values. Then you expand that, you will get a series. That's it. So let us move on to graph enumeration with the Polya's theorem. The first one, enumeration of simple graphs. Any simple graphs. Simple graphs means graphs without loops and multiple lines. So let me choose a graph G with n vertices. So there are n vertices. If there is an edge, I can connect the vertices by a edge. How many such edges possible? All possible edges will be n into n minus 1 by 2. That we know. For unadded pair of vertices. This is only for a simple undirected graph. For a directed graph, this will be n into n minus 1, because for a directed graph, A to B is different from B to A. B to A is directed from B to A. A to B is directed from A to B. So both of them are different. But for an undirected graph, A to B is same as B to A. So here it is, possible number of edges will be n into n minus 1 by 2. But for a digraph, the possible number of edges is n into n minus 1. Okay, coming to, so n vertices and we have counted the edges. Coming to this, now R. What we have dealt? We have dealt with two sets D to R. D is number of vertices of a graph G, that is n. R, a finite set, which have some weightage. So here, what about R? Here R consists of only two elements, ST. Why it is consists of only two elements? Let me explain you. It consists of two elements which are represented as weights as x to the power 1. X is given a weight of 1, t is given a weight of 0. I am giving a weightage to S and T. S with the weight 1, T with the weight 0. What's the meaning of weight 1, weight 0? Whenever the two vertices are joined by an edge, then it has weight 1. If there is no edge between any two vertices, then their weights are considered to be 0. So that's how we are giving weightage. If there exists an edge, then weight is 1. If there exists no edge, the weight is 0. So x to the power 1 is denoted by S, x to the power 0 is denoted by T. So what is my figure counting series A of x? This is the formula. So what is the possibility over here? Here x to the power 0, x to the power 1. There are only two possibilities. So I can expand only up to two elements. A0 x to the power 0 plus A1 x to the power 1. X to the power 0 is 1. A0 is number of elements with the weightage x to the power 0. How many elements are there with the weightage x to the power 0? 1 and only element. So A0 is 1. X to the power 0 is 1. 1 into 1, 1. What is A1? Number of elements with weight 1. How many elements are with weight 1? Only one element, yes. So A1 is also 1. So A1 into x. So I got A of x. Then according to Polya, after finding A of x, I have to find A of x square, A of x cube. What is A of x square then? This is A of x. What is A of x square? X is replaced by x square. 1 plus x square. What is A of x cube? 1 plus x cube. So finding all these things, you substitute these values in cycle index, you will get required counting series. So the thing is, I have to find cycle index. We know how to find cycle index. Okay, let us find. Y2 is A of x square, that is 1 plus x square. Y3 is A of x3, 1 plus x cube. Okay. Now let us move on to find cycle index for R3. We know Z of S3. What is Z of S3? Already we found Z of S3. This is Z of S3. Then what is Z of R3? R3 means paired group. So I have to find paired group of S3. What is a paired group? With a symmetric group S3, I have to find a induced permutation of all these permutations. So I have to find induced permutation. So let me try to find that, and this is the answer. This is the identity permutation of S3, and this is the paired permutation of this permutation, that is induced permutation of this one, and its cycle structure is y1 power 3. That also gives me identity. Similarly, this is the second permutation of S3, all the 6 permutations and their paired permutations and their corresponding cycle structures. Look at the cycle structures of these two. This is S3 and this is R3. Look at the corresponding structures. They are all same. So the cycle structure of S3. What is the cycle structure? Cycle index? Adding all the cycle structures. Y1 power 3. All the 3 are same. So 3 times this one, 2 times this. You are getting the same thing here also. So Z of R3 is also the same answer. Look at the cycle index of S3 and R3. Both of them are same. But this is not the case for all S4, S5, etc. Only for S3, R3 is same. Z of R3 is same. So I am using Z of R3. Now after finding Z of R3, I have to replace y1 by 1 plus x, y2 by 1 plus x square, y3 by 1 plus x cube. So 1 plus x the whole cube, y1 by 1 plus x, y2 by 1 plus x square, y3 by 1 plus x cube. Now we expand this, a plus b the whole cube, a cube, b cube, 3ab square plus 3a square b. Then you multiplying these two, multiply everything. Finally you will left with the finite series 1 plus x square plus x cube. Now what's the meaning? Actually this is x power 0. What is x? 1 into x power 0. There is no x term, that means it is x power 0. So this is for n equal to 3, that is for 3 vertices graph. How many 3 vertices graphs can be formed with 0 edges? Already I explained that x to the power 0 represents no edge. So coefficient of x to the power 0 is 1. That represents number of graphs with 0 edges. So there will be one and only graph with the 3 vertices without no edges. What is coefficient of x to the power 1? That is also 1. That means there exists one and only graph with one edge, with 3 vertices. There are 3 vertices. So there exists one and only one graph with one edge. Either you can draw like this or you can draw like this. Anyway, since it is unlabeled, everything or isomorphic, therefore they will be counted as 1. That's why the coefficient is 1 here. What is coefficient of x square? That is also 1. What's the meaning? The power 2 represents the number of edges. So number of graphs with the 2 edges. This is the only graph possible with the 2 edges. That's why the coefficient is 1. How many graphs with the 3 edges with the 3 vertices? This is the only graph. The coefficient is 1. Therefore, one and only graph is possible with 3 edges and 3 vertices. So this, from this series I can count the number of simple graphs with 3 vertices, 3 edges, 2 edges, 1 edges and 0 edge. Now let me extend this one for n equal to 4 vertices. So for n equal to 4, my b of x, that is z of R4. Z of R4 is here. This is z of S4. These are the possible cycle structures, and their corresponding induced permutations have their cycle structures as like this. Look at here, they are not same. But what we have seen in S3, both S3 and R3 has same cycle structure. But in S4 and R4, the cycle structures are not same. That's why I mentioned in S3 that both S3 and R3 has same cycle structure. But you should not expect that one for all the symmetric groups. So here they are having different cycle structure. So the cycle index for R4 is already found. So I am going to make use of this one. Z of R power 4, 1 by 24, y1. What is y1? 1 plus x. 1 plus x to the power 6. So it is 6 plus 9 times y1 square, y2 square. y1 is 1 plus x, y2 is 1 plus x square. So 1 plus x the whole square, 1 plus x square the whole square. Here it is y3. So 1 plus x cube. The power is 2. So substituting in this way, you multiply everything. You substitute like this and you multiply everything. You will be getting a series up to x power 6. That is, this represents that it is possible to draw a graph with 4 vertices and maximum of 6 edges. You cannot draw a graph with 4 vertex and 7 edges or 8 edges. That's why the series ends with x to the power 6. So how many graphs possible with 0 edges with the 4 vertices? Only one. How many graphs possible with 1 edge and 4 vertices? This one. You can draw anywhere, but if you draw 1 and 1 edge anywhere between these two vertices, means that gives a isomorphic graph. So it is represented as 1. X square, that is 2 edges. This is disconnected. This is also disconnected, but anyway, there is a common point between these two edges, but there is no intersecting vertex. They are not adjacent. Here they are adjacent. Coefficient of x cube is 3. So I came to know that there are 3 graphs possible with 4 vertices and 3 edges. 3 possible graphs. 2 connected, 1 disconnected. Everything contains only 3 edges. All of them are different. They are not isomorphic. I can draw 2 graphs with 4 edges. Yes. I can draw one and only graph with 5 edges. I can draw one and only graph with 6 edges. I cannot draw more than this. That's why my series ends with x to the power 6. So if I extend this one for n equal to 5 vertices, I will be getting a series like this. If you try to draw a graph with the 5 vertices with 0 edges, 1 edges, you will be able to identify the fact. That's all with the simple graphs. The same criteria. Let me move on to multiple graphs. Multiple graphs means a graph which allows multiple lines. What is a multiple line? 2 vertices joined by 2 different edges. That are said to be multiple lines. So what's the difference between simple graph and multiple graph? There we had only 2 elements, S, T, which the weightage is x to the power 1. Here x to the power, let me take as x to the power 0, x to the power 1. Third variable x to the power 2. What is the meaning? 2 vertices may not be adjacent. There is no edge between 2 vertices, means x to the power 0. If there is a 2 vertices joined by an edge, means their weight is 1. If 2 vertices are joined by 2 edges, means their weightage is 2. So I am going to take 3 elements in capital R, that is codomain. So now this R contains 3 elements. S, T, U. S represents x to the power 0, T represents x to the power 1, U represents x square. So what is my A of x? Figure counting series. I can expand this only up to x square. So more than that I cannot draw 3 edges. That is not a multiple graph. Only 2 edges are permitted between 2 vertex. So I can extend only up to A0, A1, A2, A0 x to the power 0, A1 x to the power 1 plus A2 x to the power 2. What is A0? The number of elements with the weightage 0. How many elements with the weightage 0? 1 and only 1. 1 and only 1 element T, 1 and only 1 element U. So all the coefficients becomes 1. So 1 plus x square. So my A of x is 1 plus x square. So what is A of x square then? Replace all x by x square. So 1 plus x square plus x to the power 4. Otherwise 2 into 2. What is A of x cube? Replace all x by x cube. That's why in general they have written A of x to the power r 1 plus x to the power r plus x to the power 2 times r, 2 times 3, 2 times 2, 2 times 4. So it's a general format. So let me substitute this one in corresponding cycle index so that you can find B of x. So what are the cycle index? We know the cycle index for R4. This is the cycle index. The same cycle index once again has been used here. But instead of y1, 1 plus x square. Instead of y2, 1 plus x square, x to the power 4, x, y3, 1 plus x cube plus x to the power 6. So the corresponding substitutions are made, and corresponding substitutions are made according to these values, and multiply everything. you will be getting a series. So for n equal to 4, that is 4 vertices, I can form a maximum of a graph with 12 edges. There is one and only one graph with 0 edge. There is a one and only graph with 1 edge. There are 3 graphs with 2 edges, 5 graphs with 3 edges, 8 graphs with 4 edges, 9 graphs with 5 edges, etc., etc., etc. So that's all with multiple lines. Coming to digraphs, we are going to count for digraphs. As I mentioned earlier, it has n into n minus 1 ordered pair of edges. Ordered pair of vertices means that represents edges. So let me use it for n equal to 4. For directed graph, Z of S4 contains this sequence and they are induced one, or these are the cycle structures, adding everything and dividing by 24. A of x is 1 plus x. Here also 1 and 2 possibilities. Either 2 vertices will be joined by an edge, or there won't be an edge between 2 vertices. These are the possibilities here also. So a of x is 1 plus x. What is a of x square? 1 plus x square. A of x cube, 1 plus x cube. So y1 is replaced by a of x to the power 1 plus x. y2 is replaced by a of x square, which is 1 plus x square. Here y3 1 plus x cube. Here y4 1 plus x power 4. The corresponding powers are raised. Once again you expand using binomial expansion, you will get a series. So there is a graph, one and only graph with 0 edges, one graph with 1 edge, and let me show the 5 graphs with 2 edges. These are the possibilities. 2 edges. All the 3 seems to be isomorphic, but look at the directions. All the 3 has different directions. So all the 3 are different. They are not isomorphic. So they will be counted thrice. This is the next 4 vertices graph with the 2 edges. This is another 4 vertices graph with the 2 edges. Here, since the direction is different in digraph, these 2 are considered as different edges, not multiple edges here. So 1, 2, 3, 4, 5 graphs with the 2 edges are possible. That's why we are getting the coefficient of x square as 5. So these are all unlabeled digraph of 4 vertices and 2 edges. In this way, I can extend this Polya's theorem to digraphs of any number of vertices. That's all with the whole syllabus and Polya's theorem. Good luck, girls.